the next class. Let's review the phenomenon of consolidation. You have a soil which is saturated with soil, and these are all the soil grains. If I just separate out, this is the solid volume, this is the fluid volume. When you apply any stress, nothing will change in terms of volume of the solids, because solids are all incompressible. It can only compress if you allow the water to go out. So here is the small outlet. If the water goes out, the volume of water in the sample decreases. And if this decreases, you get the settlement. Please remember, the initial volume is here and the sample has consolidated. The solid volume is always the same. It is only the fluid volume which is decreasing, and that decrease is controlled by the amount of water that can flow out. So this is what happening. In case of clays, you have all these particles which are plate-like, and when you apply the stress, the particles are trying to come together. They are rotating and then packing in a better way, and the water is escaping. And that is how you get the settlement. This is the analogy. I have a cylinder, I have a spring, and I have a piston. I have a small tube, but I close the valve. So when I apply the load, this is the initial condition. Cylinder filled with fluid with a spring, and here you have a pressure gauge, and the valve is closed. There is no load, there is no fluid pressure. Now you put a certain load on top, valve is still closed. Is there any way in which the water can escape? No, which means all the load is taken by the water or the fluid. So the fluid pressure is equal to the applied load P divided by the area, and that is the initial pore pressure. Now you open the valve and the water will start escaping. And if it starts escaping, then the pore pressure starts decreasing, and if the pore pressure is decreasing and the water is escaping, the load gets transferred to the spring, and then you will get the settlement. So what is happening is, this is the soil skeleton represented by the spring, and the pore water is represented by the water in the soil, and there is a transfer of stress from the water to the soil skeleton, and finally all the stress is taken by the spring and no water pressure. This is what happens in consolidation. The load is constant. The excess pore pressure is maximum equal to the total stress, and with increasing time the pore pressure decreases. If that is so, the effective stress increases. At T tending to infinity, the effective stress becomes total stress because the pore pressure is 0. And with increasing time, you get settlement. This is what happens during consolidation. So at T is equal to 0, all the applied stress is transferred through the soil, and the pore pressure is constant over the whole depth. So there is no effective stress. And with increasing time, at any intermediate time, there will be pore pressure decrease, and the decrease is maximum at the tube boundaries because this is pervious. Immediately the pore pressure drops down to 0, and you get some variation like this. And the effective stresses are maximum at the top, and then this is the effective stress. When I subtract from the total, whatever I get is the effective stress. At infinite time, as T tends to infinity, total stress again is constant, pore pressure is 0, effective stresses are equal to the total stress. This is how we say the change in volume is equal to Mv into the increase in pressure, and the continuity condition, basically it's the same. Yeah, this is the Darcy's law, and this is the continuity condition, wherein I'm saying the rate of change in volume is equal to rate of volume change, and you are equating these two, and you get your basic equation. Derivative of u with respect to time t is equal to coefficient of permeability divided by unit weight of water, coefficient of volume change, and second derivative of u with respect to z. This term k by gamma w into mv is defined as Cv, which is the coefficient of consolidation. In order to solve this, you need two boundary conditions because there are second derivative with respect to z. And because there is a derivative with respect to time t, you need one initial condition. So if I have a soil layer with pervious top and pervious bottom. I say the thickness is equal to 2H, and you can see that if this is the mid plane, water molecule from here can go to the top and the water molecule from here can go to the bottom. You do not expect water molecule from here to go to the top because the length is so high. It will always go. So this is the mid plane, and so the maximum drainage path in this case is equal to H. If I have bottom is impervious and the top is pervious, so water molecule has to go to the top because there is no way it can go down, and the maximum drainage path is equal to the thickness of the layer. Please remember, this is how we study this phenomenon. In case of one-phase drainage, the maximum drainage path is equal to the thickness. In case of two-phase drainage, maximum drainage path is equal to half the thickness. That's how we do this.